Hello, students. Thank you for joining me again. So we're still continuing on 9-4, and now we're going to look at this next corollary, or a new sort of theory that we can look at. So go ahead and read this to yourself. It just says if you have three or more parallel lines, so in this case we have three parallel lines, AE, BF, and CG, and they intersect two transversals. So they're lines that are non-parallel. So these are two transversals that eventually intersect. It's like saying A, or is it A to C and E to G are two transversals. What it says is that if these three parallel lines cut off the transversals in a way that's proportional, like let's say it cuts off A to C in such a way where the segment AB and BC make a ratio, like let's say it makes a ratio of like a third, then the other transversal that's cut will also make a ratio that is 1/3 as well, from EF to FG. So what's that going to look like? So let's just take a brief example and look at this really quick, if I can. So I'm going to try to do this with a little bit of finesse here so you can kind of see this here. So why don't we create, let's see, here. Okay, so let's create a transversal. Okay, just a random transversal, and I have three parallel lines. Actually, let's keep going farther. Three parallel lines, okay, in this way. Some of you might already kind of see what I'm trying to get at here. And I have three parallel lines going from left to right, and it's hitting this transversal. I call this A, C, and I'll call this part B. And you can kind of roughly see that, let's just say this is a line segment of 1. If you can kind of tell, B to C kind of has a line segment. Let's just say that is the length of 2. Okay? So you can kind of see if I made a ratio from AB to BC, I have a ratio of 1/2, right? Well, it does not matter for the other transversal. Let's do another transversal. Let me see if I could do it going at a much steeper slope here. And let's just say this line segment is slightly longer than 1, but it's 1.2. You got to ask, so let's just call this E to G, and then this is going to be F. Let's see how this compares to E to F. EF over FG, meaning this segment to this segment here. Well, if you can kind of make it out and see, it seems like the way that AB and BC are related as a ratio, it seems almost proportional to the way EF and FG are related to each other. Because what this says basically, here in this line, whatever ratio AB makes with BC, it should be equal to the way EF is proportional, or makes a ratio with FG. So the ratio between these segments is proportional to the way these segments are related. And if you can kind of see it by this logic, you can kind of tell. I mean, just look at my picture. This looks to be about twice as long as EF, so I'm going to call that 2.4. Now, I did make these numbers to actually fit this theorem, but you can actually kind of tell just by the accuracy of my drawing. It looks about right. This segment here and this segment here seem to be half as long as the lower parts of their transversal line lengths. So if you are actually to do 1/2 or 1.2 divided by 2.4, you'd get 1/2. So these ratios are proportional to each other, because if you had three lines going perfectly parallel to each other and you drew the transversals any way you wanted, the ratios in which the lines are cut up, the transversals are cut up, are going to be proportional to each other when you set them up as a ratio. So that's that for this corollary. And what's beautiful about that is we can go one step further in saying, hey, let's just kind of point out the obvious here, congruent parts. Not only that, let's just say if the ratio was 1-to-1, meaning you actually have transversals now going this way and this way. What if one of the transversals was cut by the parallel lines in such a way that not only is their ratio 1-to-1, but their parts that they made, A, B, and BC, are now perfectly congruent? What do you think is going to happen if I drew another random another random transversal at a completely different slope and angle? Well, EF is going to be congruent to FG. And that's exactly what we have here. If you have three parallel lines, so this is corollary number 2. It's just an extension of what we've already just previously learned. If you have three parallel lines in such a way that it creates congruent parts on a transversal, if you drew another transversal, it's going to do the same thing. It's going to cut it into two, or not just two parts that are going to make a similar ratio, but two parts that are also going to be congruent. You have AB is congruent to BC, and EF is congruent to FG. Okay, so we've already gone through the theory. Actually, yeah, let's just stop there. I think that's good. It'll set up for the last part, okay, in which we go through an example. Okay, thank you.